Hello, so in this video we are going to go over Riemann sums for definite integrals. You've seen in previous videos that the definite integral is a way to give you the area under the graph of a curve, but if that curve goes underneath the x-axis, then the integral is going to give it a negative weight, and so you don't get the area in that case. So in general you get this notion of a signed integral for the definite integral. Of course, if the function is always positive, then the integral is exactly the area under the curve. But this time we're going to use these things called Riemann sums to estimate those definite integrals. We don't have a way of computing them exactly yet, but we can estimate them using these things called Riemann sums. And remember that Riemann sums are just sums of rectangles. In other words, or sums of areas of rectangles. And it's not so bad. If you're just going to compute areas of rectangles, all you're doing is just multiplying and adding. So the math part isn't difficult. It's the idea that you really want to understand. Okay? So we're going to have two kinds of Riemann sums. The right-hand Riemann sum, right here, and the left-hand Riemann sum, right here. And notice that these formulas are exactly identical, or these expressions are exactly identical, except that the endpoints on the sums are slightly different. You'll notice for the right-hand sum, it starts at j equals 1 and goes all the way up to capital N. And the left-hand sum, it starts at j equals 0, but only goes up to n minus 1. Okay, and the explanation for this is very simple. So whenever you compute a definite integral, you're always going to be given an interval with two endpoints. In this case, let's say a and b. If you call a, which is the leftmost endpoint, t0, and b, the rightmost endpoint, t sub n, then you can make n equal subintervals in between them. So out of that big interval, you can make n smaller ones. And that number n is something that'll be given to you in the beginning of the problem. All right? So for example, in the example that we're going to go over, n is going to be equal to 4. And so you could split up, what you do is you split AB up into 4 smaller equal intervals. All right? So with that being said, let's move on to what's inside of the sum. What are the things that we're adding up? Well, just as we said before, that's just going to be the area of a certain rectangle, but which one? So that delta t, what is that quantity? That quantity is just the length. Okay, that's just the length, and it's going to be the length of each of those subintervals right here. And they're all equal, so it's just going to be some number. And of course, it'll depend on that number, capital N, that was given. And now this f of tj, well, if this thing is going to be an area, then f of tj must be your height. Sorry, the area of a rectangle. So f of tj must be your height. That tj are just those points that we use to subdivide the big interval. And so we need to know what those points are so we could plug them into the function and get the height for our rectangle. And so what rectangles are we using? We're just using rectangles that we form underneath the graph of the curve f. All right? And the Riemann sum the only thing the Riemann sum is telling us to do is to add up all the areas of those rectangles up to a certain point. So let's move on to an example so you can see how these things work for a particular function, at least. So let's say we want to find the definite integral from 0 to 2 of the function t squared. And you want to compute both of the Riemann sums, the left and the right, for the n equals 4. Capital N equals 4. So what does that mean? That means you're going to take the interval 0, 2 and split it up into 4 equal smaller intervals. All right? So you want to find the Riemann sum. We need two things. We're going to need to know the delta t, which is the length of each interval, and of course the tj's, which are the x values we're going to plug into our function that we're integrating, in this case t squared, in order to get the height. So this thing is for the length. This part is for the height. It's not exactly the height, but it's for the height. So let me put for height. This is for the length. Okay, so how are we going to do that? Well, again, let's just look at the interval 0, 2. That's the region that we're integrating over. And we want to use n equals 4. So what are we going to do? Let's split up this interval into 4 equal subintervals. So let's cut it in half first and cut it in half another time. And so in the middle we have 1, of course. In the middle of 0 and 1 we have a half, and in the middle of 1 and 2 we have 3 halves. And so you see we have 1, 2, 3, 4 subintervals, all with length delta t equals a half. So there we go. We have all of our tj's. You see t0 is 0, t1 is 1 half, t2 is 1, and t3 is 3 halves, and t4 is 2. And then delta t is a half. So now let's say the right-hand sum of that for that integral. So remember, f of t is equal to t squared. We know that delta t is equal to 1 half, and here are our tj's. So what does the right-hand sum tell us to do? It says, okay, let's form rectangles underneath the function, and of course we don't have the graph of the function here, but let's form the rectangles underneath the graph of the function, and the length of those rectangles is going to be delta t, which is a half, and if we look at the first subinterval, we're going to use the right endpoint, which in this case is, well, let's use red, 1 half. So we're going to plug 1 half into our function, t squared, so 1 half squared, and then we're going to multiply that by the length, which is 1 half. So again, how does this go? This is the height of the rectangle, 1 half is the length, and so when you multiply that, you simply get the area over region 1 of a rectangle. Okay, so let's go to region 2. Well, the right-hand endpoint in region 2, so now this part, region 2, the right-hand point is going to be 1. So we're going to plug 1, well, let's use red to be consistent. We're going to plug in 1 into the function. Function tells us to square it. Then we multiply that by the length, which is delta t, and then we multiply by 1 half. Let's go on to interval 3. We're going to do the same thing. Again, the right endpoint is, well, in this case, the right endpoint is 3 halves. So let's plug 3 halves into the function. So the function tells us to square it, and then we multiply by the length, 1 half. And finally, we go on to region 4, and we see that the right endpoint is 2. So we plug 2 into the function. Function tells us to square it, and we multiply by the length. Okay, now the Riemann sum tells us to add all the areas of these rectangles. So here's 3 and here's 4. So we're just going to add up all of those numbers. What are we going to get? Well, this is just multiplication and addition at this point. So the math part is easy. 1 half squared is 1/4 times a half is 1/8. 1 squared times 1 half is 1 half. But let's convert that to eighths, so we'll have 4/8. 3 halves squared is 9/4. 9/4 times a half is 9/8. And 2 squared times 1 half is 2, but that's equal to 16/8. So we add all of these numbers up together. 1 plus 4 plus 9, that's going to be 14. 14 plus 16 is 30. So we get 30 over 8, but let's simplify that so we get 15 over 4. There is the right-hand sum. Okay, there's the right-hand Riemann sum for the integral 0 to 2 of t squared. Let's do the left-hand sum now. Same exact thing. Function is still the same because that's the function we want to integrate. And this time, we're